Hi everyone, let's look at resistance. This is the last part for current of electricity. So you can download part 2 of the notes in your Google Classroom. So before we start, let's talk a little bit about the history of resistance. So this person here, known as Georg Siemens Ohm, he's the guy who coined the term resistance. So when electricity was first discovered, they thought that EMF or the voltage of the battery has no influence on the current that is being supplied. So they think that voltage and current are two separate entities. But Ohms here thinks otherwise. So he did a lot of experiment and tested and proved that resistance is actually related to potential difference and current. So because these two are related, he coined the term that as resistance. So the term resistance should not be difficult to understand, because if we think inside a water pump system with water pipes, okay, resistance is like adding porous plates over here, which has a lot of holes and only allow part of the water to flow through. So by putting this kind of plates, it reduces the flow of water. And it's the same as if I have a circuit, I add resistors or other components in the circuit. This will reduce the electric current flow. So the word resistance in English should be quite, in terms of layman terms, should be quite familiar to you. But in electricity, what this does is when there is resistance being added to the circuit, okay, the rate of flow of charges are reduced. Okay, and therefore current is hindered and current will drop. Okay, so now let's go to the proper definition. The definition of resistance is the ratio of the potential difference across the component to the current flowing through across the component to the current flowing through it. So it's easier to understand resistance by looking at the equation itself. R equals to V over I. So what happened is that, okay, let's look at this circuit. Okay, so Ohm should be, he did his testing. He realized that, okay, by fixing the voltage of the battery and testing different component over here, he realized that current changed. Okay, so let's say I have a material with a different material over here. The current is different. So he tested with many materials and found that different material will give different amount of current, whereas the voltage of the battery is fixed. So what restrict the flow of the current would be the resistance of the circuit, and it is given as the ratio of V over V is to I, the current, the voltage to the current. So R will be resistance, the unit is ohms, the V can be the potential difference, and I is the current across it. So to remember, you can remember it is V equals IR, or vampire in red is the acronym for it. So yeah, the omega sign is how you will write resistance. Okay, let's continue. So this is a possible circuit that is used to measure resistance, because if we don't use the multimeter, there is no component or apparatus that can measure resistance directly. So if you want to measure resistance, you have to set up a circuit like this, ammeter to measure the current and the voltmeter to measure the voltage, and simply simply calculate the resistance by taking R equals to V over I. So discovering resistance, Ohm is able to add in components to control the size of the current in the circuit, and that is known as a resistor. So in the lab, you should have actually seen these symbols before, but let me go through it properly. So for a resistor, okay, a fixed resistor, the symbol is a rectangle with two lines, and for a variable resistor, it is a rectangle with an arrow through it. So a variable resistor allow you to adjust the resistance by sliding this knob. A fixed resistor, the resistance is fixed. Like let's say you have 100 ohm, putting it into a circuit will always give you 100 ohm. let's look at Ohm's law and what he did. So Ohm's law states that the current passing through a metallic conductor is directly proportional to the potential difference across it, provided that the physical conditions remain constant. So basically what he did was he conducted many experiments with different with the same material but different potential difference of different EMF, and he realized that the current changes accordingly. So basically using different voltage, he noticed that current varies linearly, and it's not just linear, it's directly proportional. So increasing the voltage also increased the current. So this is very wonderful because we know that resistance is V over I is given as resistance is coined as R equals to V over I. So having that this is a directly proportional means that the resistance of the circuit is constant. Okay, so if I take V over I at any portion of this graph, I should have the fixed resistance. So in the lab, this is what we did. We actually verified Ohm's law, but of course we plot a graph of V against A instead of I against V. Sorry, V against I instead of I against V. So it's the same. Basically, you get a straight line graph, and in that experiment, you notice that the gradient is always 2. Okay, in that case, the gradient that in that graph would represent the ratio at any one point is which is V over I is always 2, which means that the resistance is always 2 ohm. So this verifies Ohm's law, saying that for a metallic conductor, the current is directly proportional to the potential difference. Okay, of course, there's a caveat here saying that the physical conditions remain constant. Later, I'll talk about what do I mean by this. So what you have here is, just now I mentioned in the previous slide that I have a fixed resistor, let's say it's 100 ohm. So placing a fixed resistor in a circuit should allow the circuit to have a fixed resistance all the time without it changing much, because we know that it obeys Ohm's law. So that is a good thing. So now, a possible question that they can set in exam is which graph doesn't obey Ohm's law. I think this is quite straightforward. As long as it's a straight line and passes through the origin, it should obey Ohm's law. The rest does not obey Ohm's law, does not, and does not. Okay, so it's very clear cut that it must be directly proportional to the V must be directly proportional to the current. So there are conductors that don't obey Ohm's law, but conductors that obey Ohm's law is known as an ohmic conductor. So that resistor that you use in the lab is considered an ohmic conductor because in the IV graph or VI graph that you plotted is a straight line and it should pass through the origin. So there are also conductors that do not obey Ohm's law, and one of them is known as the filament lamp. So for the filament lamp, if you plot the graph, IV graph, you can ignore the negative part. Okay, you will notice that at the front part, it obeys Ohm's law because it's a straight line. So resistance when current is low or when the potential difference is low, the resistance is pretty much constant. But as the current increases, or if you supply higher voltage, you notice the current will of course get bigger, but notice this part is curved. So if I take V over I, then the R equals to V over I, the resistance would have been higher at this particular portion, okay? Because the increase in V is steadily increasing, but I only increases a little bit. Okay, so this is a filament IV graph. And another type of component that is non-ohmic is the diode. There's many different types of diodes, and one of the common ones we talk about is the LED. So the LED bulb, the LED bulb only allows current to go if the current is flowing in the same direction as this arrow over here. So let me draw out a circuit to explain. So when you connect the LED bulb, apologies, the current follows the arrow of the diode, then this diode will light up. Okay, so if the current is opposite, then this whole diode will not work. So what happened is, at this part, this is if you connect the current in the opposite direction, the resistance is very high. So if you look at it in terms of a VI ratio, this part is very high, and any voltage below 0.6 volt, the resistance is very high also. But when it's after 0.6 volt, the resistance is very low. So always remember that resistance is taken as V over I, and this is an IV graph, so you have to switch around and look at it in the opposite sense. So LED bulb only lights up if you connect it correctly. So if this is an LED bulb, this is the plus and this is the minus. So if you connect the plus to and the minus in the wrong side of the circuit, you actually will not have the LED bulb lights up, but it doesn't mean that it is spoiled. So these are two possible non-ohmic conductors, so they do not obey Ohm's law. So just now I mentioned that in a filament lamp, the resistance changes as the current increases. So let's look at why this is the case.
The property of absorbing rather than transporting the current, Ohm termed resistance. This resistance causes the conductor to warm up. The electrons flow along the wire. In the process, they bump into the particles that compose the conductor. The more of these particles that get in the way, the fewer electrons can get through, and the higher the resistance of that particular conductor. Every collision slows the electrons down. They lose energy, which is given off in the form of heat. Given the right material, a very thin wire can glow white hot in this way. In the incandescent lamp, this effect is exploited for lighting purposes.
In the final part of resistance, we are going to look at something known as the resistivity. So other than temperature, this resistance of a conductor also depends on a few other factors. So one is its length. So the longer the conductor, the more resistance it has. The cross-sectional area, that means, let's say if I have a wire, so how thick is the wire or how thin is the wire will affect the resistance as well. And then the resistivity, and that depends on the material it is made of. So let's say I have a conductor over here. The resistance of this conductor can be calculated with rho L over A. So when we say resistance is R equals to V over I, we are looking at the resistance of the whole circuit itself. But if we have a conductor and we know its dimension and all its other physical properties, we can also calculate its resistance. So how do we remember this formula, or how do we relate between length, cross-sectional area, and how it affects resistance? We can think of it as how you would drink bubble tea. So many years ago, I decided to get a koi, and I liked the grass jelly milk tea with pearl. And I took some pictures. Okay, so which is the best way to drink koi, and why haven't we considered other options? So when you buy a bubble tea, you know that the straw is pretty thick, and it's reasonably long and not too long or too short. Okay, so that you can drink. So in this first scenario, I use 3 different straws and try to drink. Okay, so if you try to use the Yakult straw to drink, it's thin and short. Okay, so you will have more issue trying to drink this, and you can't get the pearl or the glass jelly in. Okay, how about a long bubble tea straw? So I actually combined 2 bubble tea straws together to form a very, very long straw. Okay, and same thing. Okay, I will have issues sucking out the pearl and the water itself. And what about a McDonald's straw? So McDonald's straw is thin and long, much longer than a bubble tea straw. So I also have issues drinking as well. So what I'm trying to point out here is that basically for a conductor, the wider and shorter it is, the better it is to conduct electricity. So a long and thin wire or a conductor has the most resistance, okay, and these two are in between, while a conductor that is thicker, okay, or we can say that a wire that is thicker and shorter has the least resistance. So it has the best conductivity. Okay, so here we can look at 3 different samples. So this is the original one. So other than the thickness, the cross-sectional area or the thickness, the length, the material that makes up the wire also matters. So if this wire has something, the arrangement of the atoms and all that restrict the flow of the current, we say that it has bigger resistivity. So then it will affect the current flow, so it has bigger resistance. So note that cross-sectional area is inversely proportional to the resistance. So bigger cross-sectional area, the resistance actually is lower. So you do see that there is a bigger path, wider path for the current to flow. And longer length means it needs to travel a longer distance, therefore resistance will be higher. So just now the formula, let's go back again, is given as R equals to rho L over A, where rho this time is not the density but the resistivity, L is the length, and over A, okay, which is a cross-sectional area. If I rewrite this formula to just calculate resistivity, then I will have RA over L. So the unit for resistivity is ohm meter. So just to reiterate again, resistivity is a property of the material and is independent of the dimensions of the material itself. You can think of it like density or the specific heat capacity of the material. So resistivity is basically how the material would resist current if a potential difference is applied across it. So the lower the resistivity, the better it is at conducting electricity. So we have some materials over here. So silver and copper basically have very low resistivity. So it means that it is a very good conductor of electricity as compared to tungsten or nichrome. And you can see that plastic actually have so high resistivity that basically it is almost impossible to conduct any to have current passing through it, whereas this is so much lower. So once again, if the resistivity is pretty high, I mean comparatively high, then you will actually get when this is made, let's say nichrome is made into the wire, then this wire would actually have more resistance, and therefore it is more likely to heat up. So remember graphite? Yeah, we did try to conduct electricity through graphite, and you notice that the bulb did not light up. So you can see that graphite has so much higher resistivity, 3000, okay, 3000 times more than a copper. So the graphite pencil that you use doesn't allow the current to pass through so easily. So that's why the bulb did not light up. Yeah. So so with this, you should be able to do the class exercise and also the assignment. So just to sum up, we have we talk about current, we talk about potential difference in EMF, which is the voltage. So let me just bring this down. So this is the voltage, and we have current, and voltage, and then we have resistance. So the first formula that we look at is Q equals IT. The second formula that we look at is W equals to VQ. We can ignore this formula, which is the EMF, because they are the same thing. And the last formula that is more of importance is V equals to IR. And of course, to calculate the resistivity, or if we want to find resistance based on resistivity, is R equals to rho L over A. So this particular formula is very niche. That means that if this question comes out, you will know that you have to use this formula. Whereas V equals IR, Q equals IT, and W equals VQ can be combine into one single question itself. So you need to know when to use which one, depending on the situation. You'll see this more in your class exercise and on the topic of DC circuit. So please go back and try the assignment, and you will need to submit it online. Okay, and that's all for resistance.